Brendan Howell that hard over on it. I like when you say
That does not seem safe.
That's okay.
Seems a little more safe.
Steve Todd.
All right. Today we're going to talk briefly about power. A pretty quick and relatively easy way to wrap the energy and work chapter up. Power is divided, it's the rate at which you do work. So it's work is putting energy in or taking energy out, or it's converting energy. So really what this is it's the rate that energy is converted from one form to another, often by a machine or by us or whatever. We have a formula. Since it's the rate, that means how quickly. We have a work over time. And that's it. So if you can calculate how much work is done, just divide it by how long it took in seconds, and you're good. Units here is a joule per second. We made up a new unit for this, which is a watt. I said watt. After James Watt, the steam engine guy. There's one other special way or easier way to look at this, and we can figure that out on the units. What is a joule? How else can we express it, I should have said.
Force times displacement.
It's force times displacement. So this would also be equal to a Newton times a meter, which is a joule, over a second. And all I'm going to do is rearrange that slightly. Like so. A Newton times a meter per second. So if we want to find power, that implies another way of doing things. We could take a force measured in newtons. What is this?
Velocity.
The velocity. And this would be just like before. We're not going to get into difficult ones, but this would be force times the speed times the cosine of the angle between them. But for our purposes, we can, I think all the things we're going to be doing they're all in the same direction, so we don't have to worry about it. So we have two ways to express power. Here's number 2. Here's number 1. And I don't want to talk you through a whole bunch of other stuff, but because we'll have work time, and I don't want to talk today. Yes, Mark.
So what is a horsepower?
Horsepower. I forget. Let's check. That's a different unit of power, and I forget exactly how much it is.
Like foot-pounds or something like that.
Yeah, that's usually torque. So 745 watts is 1 horsepower. So horsepower is quite large. We use horsepower in the US and watts, of course, because it's the same amount of power that's used up by electrical things. So if you have a 60 watt light bulb, that means it's converting 60 joules of electrical energy into heat and light every second. Another way of putting that is if you have this 1 kilogram mass, that 60 watts is equivalent to raising this about 6 meters up, right? That's about how much potential energy you'd be putting into it. So around 40 feet every second.
one watt raises that 1 kilogram weight 6 meters.
So it's, no, not 1 watt. 60 watts. 1 watt, if we look at it that way,
Report for it. The screen.
why? It was working just a minute ago. There we are. If we wanted to look at that, we'd say, okay, well, how much energy would that be? And that'd be a potential energy, right? So 1 watt is equal to the potential energy, M times G times H over 1 second. So we'd have 1 joule here multiplying a second by a watt is equal to 1 kilogram times 9.8 meters per second squared times whatever height we can do it. If we divide through this, this is about 1 over 10. So about 0.1 meters is 1 watt. So it takes 1 watt to lift it from there to there in a second. So that's not that much. But when we start talking about household usage, and you start putting it in terms of how high would I have to lift this, then it starts to add up pretty quickly. Because that's 60 watt light bulb is 60 joules every second for each 60 watt bulb that's on. And that adds up pretty quick. Okay, we've got a homework on this. I'm going to stop talking, go to work, and I'll come around and check off homeworks and things.